On to some additional experimental designs that are commonly used in the field of behavior analysis: changing criterion designs and multiple baseline designs. First, multiple baseline designs. When displayed graphically, these produce a staggered or tiered set of baselines. When an intervention is put into place after the first tier's baseline, tiers 2 and 3 are kept in baseline. That way, as long as the Tier 2 and Tier 3 baseline data remain stable while the Tier 1 intervention data change, we have some verification that the change in Tier 1 was actually because of the intervention. Then, when an intervention is then put into place following Tier 2's baseline, Tier 3 is still in baseline, another opportunity for verification. There are three primary types of multiple baseline designs. First, across behaviors. In this case, you assess the effects of the independent variable on multiple different behaviors of the same participant that are in some way similar. Second, across settings. In this case, you assess the effects of the independent variable on the same behavior of the same participants, but in multiple different environments. Note that setting can be the same setting, but where there's some change made, such as a new person being present, like a different staff member. Finally, across participants. In this case, you assess the effects of the independent variable on the same behavior of multiple different participants. In each case, there must be a chance of extraneous variables affecting behavior in the same way in all tiers. That is the only way that we can assess the potential influence of those extraneous variables, and thus allow for the opportunity of verification. We'll discuss the importance of this later in the slideshow. As stated on the previous slide, in order for baseline logic to be fulfilled, in each design there must be a chance of extraneous variables affecting behavior in the same way in all tiers. This means that the different behaviors must be measured concurrently, not sequentially. If the baseline and intervention phases do not overlap, as shown in this picture here, we have no evidence regarding whether an extraneous variable may have affected one or both behaviors. In this case, the two behaviors are being measured concurrently. This meets the requirement of a multiple baseline design. Note, however, that the behaviors must also share some similarity, whether in terms of topography or function, for there to be a good chance of both the independent variable and potential extraneous variables affecting them similarly. Similarly, in the case of a multiple baseline design across settings, the settings must be distinct enough for there to be differentiation between them, but also similar to the extent that the target behavior can occur reliably in all of them. Our biggest difficulties arrive with an across participants design. In this case, we can't argue that a participant is acting as their own control, as we do with most single subject designs. Instead, we simply have a sequence of A-B designs. However, we have at least better experimental control if we ensure that all participants are in the same environment at the same time, and thus their behavior is subject to the same environmental variables. Note that Cooper, Heron, and Heward discuss these requirements in terms of 1, selecting independent yet functionally similar baselines, and 2, the necessity of selecting concurrent and plausibly related multiple baselines. Before deciding on the use of a multiple baseline design, be sure to review their guidelines in Chapter 9. One recommendation for the use of multiple baseline designs is to vary the length of each baseline. If all baselines are equal in length, changes in the dependent variable could be attributed to confounding variables, such as practice or reactivity to the observation and measurement procedures, and not to the independent variable. Second, intervene on the most stable baseline first. This allows for some demonstration of control, even when the intervention must be started right away in an applied setting. Remember to still only do this when all, or at least the majority of baselines show reasonably stable steady-state responding. Here you see an example of a multiple baseline design across participants. Baseline data are collected concurrently for all 3 participants. That is, we collect data on the behavior of all 3 participants at the same time. When steady-state responding is achieved in all 3 tiers, intervention is introduced to Tier 1. Again, once we see steady-state responding in all 3 tiers, the intervention is then introduced to the second participant in Tier 2. Finally, we wait for steady-state responding again and introduce intervention to Tier 3. Here's an example of a multiple baseline design across behaviors. This design operates the same as a multiple baseline design across participants, but we're targeting 3 different behaviors, reading, a campfire project, and clarinet practice, instead of the same behavior of 3 different participants. Note that the behaviors should be similar in some way. Again, there has to be the chance of the intervention implemented in Tier 1 affecting the behaviors in Tiers 2 and 3, or for extraneous variables to affect all of the behaviors similarly. In this case, time spent completing different types of homework projects was measured. Here's another example of a multiple baseline design across behaviors. Note that there are multiple participants in this study, learner 1 and learner 2, but we're assessing the intervention's effects across each learner's different behaviors. It's possible to have multiple participants involved in a study or intervention utilizing a multiple baseline design, without the design necessarily being a multiple baseline across participants. Here's one more example of a multiple baseline design across participants. Let's start to think about how this design can show a functional relation. Based on the increased variability in Ross's responding that begins when the intervention is implemented for Kate, you might argue that whatever is affecting Kate's behavior could be affecting Ross's to some degree as well. This means that while we do have evidence of verification in Mike's and Walt's data that it was indeed the intervention that affected Kate's data, the fact that Ross's data changed at the same time as Kate's without implementation of the intervention is some evidence against verification. There is, however, a more distinct change in Ross's behavior when the intervention is implemented at his tier. This, combined with the replication across participants in the case of Mike and Walt, should make us fairly confident in the presence of a functional relation between the dependent variable and independent variable. Ultimately, multiple baseline designs are best used when changes to the target behavior are irreversible. Remember, in the case of a reversal design, when we return to baseline, it's possible that what was learned during intervention doesn't actually reverse, so we can't show a functional relation that way. Just to elaborate a bit on this, one example of an irreversible change is learning a new skill. Dr. Gregory Kimball in 1961 defined this as a relatively permanent change in a behavioral potentiality that occurs as a result of reinforced practice. For example, a child reads a book and there are difficult words. The teacher underlines difficult words with a red pen and then later removes the underlines in a return to baseline. If the child learned to read those difficult words during intervention, it will be unlikely for the dependent variable to return to baseline levels, so we won't be able to show a functional relation with a reversal design. A multiple baseline doesn't include a reversal. It endeavors to show a functional relation in other ways. This design is also preferred when returning to baseline, removing treatment, would be deemed unethical, or is impractical, or not otherwise desired. Again, you can see that this addresses some of the concerns of a reversal design. Multiple baseline designs across behaviors and environments are useful for situations in which multiple changes are desired. It's an efficient way to stagger intervention and assess the effects. Given that the design must allow for the effects of the independent variable to generalize across tiers, the design is a good way for assessing that effect. This is a good socially significant result, but note that it does prevent you from showing a functional relation, since we don't see clear verification. Similarly, assessing the effects of the independent variable on multiple behaviors in multiple environments, or on the behavior of multiple participants in a single environment, can allow thorough test of an intervention's efficacy before then applying that intervention on a larger scale. Multiple baseline experimental designs have become very commonly used in ABA, since they don't require removal or reversal of the intervention or alternation between multiple different interventions. Unfortunately, it's not all positive. They often suffer from some of the same problems as AB designs unless they're implemented very carefully. Perhaps most importantly, when it comes to truly demonstrating a functional relation between variables, multiple baseline designs across participants are not true single-subject research designs, as Cooper, Heron, and Heward note on page 209. There's no opportunity for within-subject replication of phase and effects. This is more of a cautionary note about how to create a good multiple baseline design, but again, there has to be some possibility that a change to Tier 1 could change behavior in Tier 2 and 3, etc. If a treatment for one participant in one setting bears no relation to treatment applied to another participant in another setting, you won't have a valid design. Finally, while waiting for steady-state responding across tiers, one participant or behavior may remain in baseline without access to intervention. This bears the same ethical concern as waiting for steady-state responding during a reversal design. Let's look at an example of a multiple baseline design across settings. You want to evaluate the effectiveness of a strategy to increase the extent to which a teacher's assistant, Sheila, interacts positively with students. You want to try out the strategy on a limited basis in your own classroom before recommending that other teachers use it. First, collect baseline data on the percentage of intervals with positive interactions in the classroom. After stable baseline levels are obtained, implement the intervention, the independent variable, in Classroom 1, but continue with baseline in Classroom 2. When steady-state responding is observed in Classroom 1 and Classroom 2, then the same intervention can be implemented in Classroom 2. Our design has allowed us to show experimental control and identify a functional relation. In the case of prediction, if the independent variable had no effect on the dependent variable, we would predict that the percentage of intervals with positive interactions in Classroom 1 wouldn't change following the introduction of the independent variable. The same would be true of a change following the introduction of the independent variable in Classroom 2. But we do see a change following the intervention implementation in both tiers, so we have some evidence of a functional relation. If the dependent variable remains steady in the other tiers of the design in which the independent variable has not been implemented, we help to verify that the change following the independent variable in the first tier was not due to coincidence. Normally, we would want to assess whether, when we remove the independent variable, performance is then similar to our original assessment. We don't do this in a multiple baseline design. Instead, we verify that the other baseline performance remains stable, even when intervention is implemented following the first tier's baseline. If we see that performance in the other tiers changes at the same time as the independent variable is implemented in the first tier, we don't have evidence of a functional relation. In the case of a multiple baseline design across settings, behavior in both environments may have changed at the same time as a function of some other extraneous variable, or there may have been generalization across environments. If we see the same effect on the dependent variable in the other tiers when and only when the independent variable is implemented, we have replicated the effects of the independent variable. Even if behavior doesn't change in the second, third, etc. tiers during baseline, it's still possible that an extraneous variable affected behavior in the first tier when the independent variable was manipulated. We still want to see replication across the different tiers as evidence of a functional relation. Replication within phases is represented by each subsequent data point with steady-state responding. We also see replication across tiers, either participants, behaviors, or settings, when we see the same effect on the dependent variable in the other tiers when, and again only when, the independent variable is manipulated. The more tiers we have in a multiple baseline design, the more evidence we have for a functional relation. Note, however, that we're not ever going to be able to see replication across phases in a single tier. One variation on this design is a delayed multiple baseline. After the initial baseline and intervention are started, other baselines are added in a delayed fashion. This design uses the same logical reasoning as a regular multiple baseline design, but baselines started after intervention cannot be used to verify earlier predictions. In order to allow for demonstration of a functional relation, some baseline measures across tiers still must overlap. You might use this design if you can't collect data on all tiers at the beginning of a study, but can add additional tiers later. You might also use this design if, in the words of Cooper, Heron, and Heward, a new behavior, setting, or subject becomes available. You initially begin collecting baseline and intervention data as if you were implementing a different experimental design, but then find it valuable to intervene on those additional tiers. Another variation is a multiple probe design, rather than a multiple baseline. This is again very similar to the basic design, but the dependent variable is probed rather than assessed with more continuous measures. With this design, you can evaluate the effects of interventions designed to teach a sequence or chain of responses. That may be preferable when continuous measurement is impractical or would lead to reactivity. Note that this design means that you still must obtain a baseline assessment in later tiers that overlaps with both phases of earlier tiers. This allows you to determine whether the dependent variable in those later tiers changes at the same time as intervention in the earlier tiers. If it does, you do not have good evidence for a functional relation. For example, Sam is teaching Fiona how to do the polka and wants to assess his teaching method of total task presentation with most to least prompting. If Sam carries out 10 baseline sessions, it's likely that Fiona will learn it a little bit during these sessions just by having the opportunity to observe and/or practice, even without feedback and prompting. This means that we have a confounding variable, and the baseline data may show an upward trend. Also, it won't take Sam 10 baseline sessions to figure out that Fiona has absolutely no clue how to do the polka. There's no need to risk these continuous measures. Probes would be absolutely fine. Here's an example of a multiple probe design across behaviors. You can see, based on the black data points during the baseline phases of each tier, that the target behaviors are not continually assessed, but instead are only probed. The behavior in each tier is probed each time a phase change is changed in another tier. Here's another example of a multiple probe design across behaviors. You can see that many tiers and many phases can be included in a single design. The other design that we'll cover today is the changing criterion design. According to Cooper et al., changing criterion designs can be used to evaluate the effects of a treatment that is applied in a gradual or stepwise fashion to a single target behavior. When stable responding is attained with each phase of the design, a prediction of future responding is made. Replication occurs each time the level of behavior changes in a systematic way when the criterion is changed. And verification of the predictions based on each phase is not so obvious in this design. However, if you vary the length of each phase, you can verify that behavior maintains at a given criterion as long as it is not changed. You can also embed a reversal design and return to a previous criterion level. We'll discuss this shortly. The essential rule for a changing criterion design is to establish stable responding at baseline and prior to implementing any new criterion. The criterion at each level is considered met if responding matches or exceeds that criterion. If the dependent variable changes when and only when the independent variable is manipulated, a functional relation is shown. Here are the baseline logic guidelines for the changing criterion design. For prediction, consider each phase to be a baseline for the next phase. If the level maintains in the next phase, there's not a functional relation. We see replication if each stepwise change in criterion level results in behavior change to that new level. We can see verification of our predictions with a couple of additions to the design. Successful implementation of the changing criterion design requires particular attention to 3 design factors: length of baseline and treatment phases, magnitude of changes in the criterion, and number of treatment phases or changes in criterion. In other words, the length of phases and the magnitude of changes in criterion should be varied within a single design. The more phases or changes in criterion there are, the more evidence you'll have for a functional relation. Another factor to improve the strength of your design is to actually decrease your criterion for one phase if you've previously been increasing it. If the dependent variable changes to match the new criterion, you have very good evidence that it's a function of the criterion itself and not some other variable. Here's an example of a case in which a changing criterion design could be ideal. You want to help Michael spend more time studying. Currently, he does not study until right before a quiz. His goal is to study for 45 minutes per day. How would you set up and evaluate the effectiveness of a self-management procedure to help him? Here are some sample data from the scenario we discussed. First, we wait for steady state responding. Michael isn't studying at all. We set a daily criterion of studying for 15 minutes. Michael doesn't meet the goal right away, but then does for 3 days in a row, meeting steady state responding requirements. So we increase the criterion again to 30 minutes per day. That goal is met in a similar manner. The goal is finally increased to 45 minutes per day and is met, immediately. Here's an example of a changing criterion design showing a pretty clear functional relation. Since we've waited for steady-state responding at each criterion level, we can see that behavior does not change in level or trend until that criterion is changed. Thus, we have multiple opportunities for prediction and replication. Here's a changing criterion design with the criterion decreasing rather than increasing. In this case, we see the behavior trending downward more dramatically at the 60 and 40 criterion levels. So the criterion was changed with a large step size each time. When we get down to a criterion of 20, behavior levels out, so the step size used from there on out is smaller in order to avoid ratio strain. Here we see that when we set a criterion following baseline indicated by the red line, behavior did not change very much. What seems to be occurring in this scenario? We set a criterion that was, for whatever reason, not met. Perhaps the increase in level was too high, and we encountered ratio strain, such that the behavior was ultimately extinguished. When setting each new criterion, one option is to base it on the variability or range of behavior in the previous phase. For example, in the third phase here, the goal is marked by the red line, but behavior in some cases exceeds the goal. We know then that we can safely set the next criterion level at least that high. You could ultimately choose to simply increase the goal by a certain proportion each time, but know that if the goal isn't met, you may need to step it back and build up to it more gradually. Another concern when setting a criterion is not setting it such that it can't be exceeded. Cooper, Heron, and Heward note that if you give a student only 5 math problems to complete when the criterion for reinforcement is 5, although the student could complete fewer than 5 problems, the possibility of exceeding the criterion has been eliminated, resulting perhaps in an impressive-looking graph, but one that is badly affected by poor experimental procedures. The number of total criterion changes in a design contributes to demonstration of a functional relation. From page 222, the more times the behavior changes to meet the new criteria, the more convincing the demonstration of experimental control is. However, keep in mind that in deciding the length of each treatment phase, clinician researchers must also remain sensitive to their clients' needs and not hold clients at a criterion longer than would be wise therapeutically. In other words, don't keep the participant or client in a phase forever. If a given criterion isn't being met, the independent variable should be manipulated such that the criterion is decreased or additional intervention is provided. Again, instead of using a very long design, including many criterion changes, a great alternative point of evidence for a functional relation would be to do reversals to prior levels and see if behavior tracks those reversals. As with last week, we'll practice more with identifying examples of experimental designs, deciding when to use the different experimental designs, and graphing data in different experimental designs in class.